So we've been doing particle kinetics, and now we're going on to rigid body kinetics. I guess anybody have any homework questions before I start the new stuff? Do you have it there? Oh, I have it. Number 3. Ferris wheel. Okay, particle kinetics number 3. A Ferris wheel has a radius of 4.5 meters. It rotates with a constant angular speed of 1.2 radians per second. It's on a train car. Which is speeding up at 2.5 meters per second squared. Oh, path of the train car is perpendicular. Okay, so now it's just well, I erased it anyways. Okay, so it's not going that way. It's going this way, like, let's say, into the page. Speeding up at 2.5 meters per second squared. And a vector, let's say it's going into the page, so that's the arrow, the feathers of the arrow of the vector. And it doesn't say anything about which direction the Ferris wheel is moving. So I'll say counterclockwise with an angular speed of 1.2 radians per second. And we need a coordinate system. So I'll say the z-axis is coming out, x is to the right, y is up. And the point that we're interested in is right here. That is a 50 kilogram passenger, and we're trying to figure out the acceleration while we're trying to figure out the net force. What's the net force on the passenger at P? The acceleration of the passenger. Okay, well, let me start from what the question is. So the question's asking for the net force. So we're going to use Newton's second law. And that says that F net is equal to the mass of the passenger times the acceleration of the passenger's center of mass. And this acceleration has to be in an inertial coordinate system. So if our coordinate system is moving with the train car, then its origin is accelerating, and that's not inertial. So we can't do that. So we need to use relative motion. It's really the same kind of idea as that problem I did at the end of class last time. I mean, using the relative motion equations. So the acceleration of the passenger relative to the ground is equal to the acceleration of the passenger relative to the train plus the acceleration of the train relative to the ground. The acceleration of the train relative to the ground is what's given. So that acceleration is 2.5 meters per second squared into the page. That's the negative z direction, the way I have it drawn. So that's 0, 0, negative 2.5. And the passenger relative to the train, this is circular motion. So this is equal to all ripe watermelons will rot. It's moving with a constant angular velocity, and so this one goes away, and we're just left with the centripetal acceleration. So the acceleration of the passenger relative to the train is, I have my angular velocity in the positive z direction. The r vector from the center of the circular motion to the point that you care about. So that's 4.5 meters in the negative y direction. So this is equal to 0, 0, 1.2 crossed with the quantity 0, 0, 1.2 cross 0, negative 4.5, 0. So that is 5.4, positive 5.400, right? Crossed with 0, 0, 1.2. And that is 0 for x, 0 for z. And then in the y direction, 6, 60. What do you get for that? 64.8 or 6.48? Is that right? 64.8. 6.48. That's meters per second squared. And so the acceleration of the passenger relative to the ground is 6.480 plus 0, 0, negative 2.5. That's 0, 6.48, negative 2.5. And now that's an acceleration in an inertial coordinate system. So now we can use Newton's second law. And Newton's second law, if there's no reason to draw a free body diagram if you're just trying to calculate the net force. That's the only time you don't have to draw a free body diagram. So the mass of the person is 50. So 50 times this acceleration zero. 32.4, 324. and negative 125 newtons.
You want all this work done in that form. You don't want like omega squared times. There's just a shorter equation, non-vector.
No, I'd get used to doing this because the nice thing about this, so like those of you who got to this stuff in physics 1, it's sort of at the end of the semester. Yeah, you do it all in terms of omega squared r and all this stuff, these scalar equations, and then you have to think about the directions yourself. This does the directions for you. You know, I think the reason that you don't do it this way in physics 1 is because you haven't done a lot of stuff with vectors yet, and I think maybe it would be best to do this from the start. But this does all the directions for you. So it really, in a way, as long as the cross products make sense and stuff, this is an easier way to do it, I think. Yeah. Yeah, but the center is moving with the train. So you can think of you know the so the Ferris wheel is mounted to this axle goes through the Ferris wheel that's attached to the train. And so that's all one rigid thing. And then the wheel moves around the center. So really that's just naming. I could have called that the center. But yes, you're exactly right. It's the key thing there is the reason that this is circular motion is that the acceleration of the passenger relative to the train is the same as the acceleration of the passenger relative to the center. That's right. Any other questions about this? Any other homework questions? Did anyone get to that sort of souped up version of the problem we did on Friday? Did I assign that? How far into these have I assigned? Oh, okay. Okay. Well, that'll come in 6 and 7. Let me say something about those. Okay, so in this one, you have a block and tackle system. Um, so you have a pulley like that, and hanging pulley with a mass of, and this one has a mass of 150 kilograms. Well, those need straight up and down for what I'm going to say. Um, and then this one has a mass of 100 kilograms. And let's say we want to know what's the acceleration of the 100 kilogram. Well, your first thought, I mean, if this 150 was just hanging over the other end of this cable, the 100 kilogram mass would accelerate up, right? Um, but if you have the system set up like this in a block and tackle system, I'll show you why it turns out that the 100 kilogram mass is actually going to accelerate down. It's pretty cool how it works if you haven't seen this physics of this before. They use this a lot in like any kind of shipping yard where they have to pull big containers around train stations or like into Luth. You see these hooked up, putting stuff in the shift. So if you have something really big you want to lift here, you rig up a system like this, and you can do it with a lot more pulleys and get a lot better, bigger effect than we're going to get here. But the effect of setting it up like this, with a hanging pulley being supported by a pulley system that goes from the ceiling, through the hanging pulley and stuff, is that you can lift a bigger weight with a smaller weight, or in other words, you can apply a bigger force with a smaller force, which obviously is nice if you're, if this isn't 100-kilogram mass, instead it's your hands or some machine that you need to build to lift it. It's nice to not have to lift so much. There's a trade-off for it. So you're getting this extra lifting strength, but you can't get energy for free. There's conservation of energy, and so the trade-off is that in order to lift this an inch, you have to pull this down 2 inches. And the explanation for that, and this is actually comes into the equation, once we get to the part of these kind of problems where we have to come up with our constraint equations, remember when we just had 2 masses hanging over 1 pulley? Our constraint equation said the acceleration up of one of them was equal to the acceleration down of the other one. We have something like that here, but it's not 1-to-1 like that. So now, in order to lift this up a half an inch, you have to pull this down an inch. And that same effect transfers to velocities and accelerations. And so the acceleration, let's say the acceleration down of the 100-kilogram mass is twice the acceleration up of the 150-kilogram mass. Okay. And to make physical sense out of that, you can think of the fact that when you're lifting this up, okay, to lift this up, let's say to lift this up 1 inch, okay, you have to shorten this length an inch, and you have to shorten this length an inch, okay? And where does that go? They both go into here. So this has to come down 2 inches. Yep, exactly. So the way the conservation of energy stuff works, remember work is force times distance. And so if you make the force 1/8 as big, you have to make the distance 8 times as big. Okay, so let's draw a free body diagram of everything that's hanging by the cable. So there's the 150-kilogram mass. There's the pulley. And the forces applied are a downward force. 150 times 9.81 is 1471.5. And then the only other place there's contact, and I think I'm sort of glossing over this. What we're really doing is we're isolating the mass and the pulley and the section of this cable that goes from here to here. So maybe let me draw that a little more carefully. It's like bat signal. So all of the cable in here is being isolated in our system. Doesn't change our mass because we're assuming that that cable is massless. Okay, so now where does the outside world make contact with what we've isolated? Where I cut off the cables. And so there are cable tension forces here, and here. And since it's the same cable going through frictionless, massless pulleys, these are the same. And so Newton's second law says 0t plus 0 negative 1471.5 is equal to mass 150 times the acceleration, and we know that's in the y direction. We don't have to specify direction. We can just call it, a 150. And so then when you go to do the, the next thing is you isolate the 100. I'm not going to do that. And then the last step is the constraint equations. And in this case, that just says that A100 is negative 2 A150. They're in opposite directions, and the 100 is accelerating twice as much as the 150. And you can sort of see where this benefit comes from maybe here. If you, let's think about it just in terms of statics. Okay. So all we're doing is trying to make this hang here. We want to see like what's the cable tension that you have to have. Okay. Like this is attached to the floor or something, and we just want to see what the cable tension is. If you just had this cable going over the pulley, one pulley and attached to the floor, then the tension in the cable would be the weight of the thing that it's holding up, so it would be 1471. Now, because we have these two cable forces, this would be half of 1471 if it was static. It's not going to be that here because of the acceleration. And so if you rigged something up like this, so now this is the big mass, and the cable went through here, through here, through here, through here, and then attached to the 100. You get more effect because when you took the free body diagram of all the hanging stuff, you'd have 1471.5 pound, the weight of this, and then you'd have 4 cable tensions. And so if it's static, you're just dividing that weight by 4. The more of these vertical cables you have connected to your hanging thing, the more you reduce the weight. At some point, friction catches up with the benefit of adding more pulleys, so there's sort of an optimal number depending on what pulleys you have. But if you're ever in the physics lab with me and you can't think of anything witty to say or whatever, ask me if, like, we have pulleys and stuff. It'll take 2 minutes to rig this up and hang a weight to it, and you can actually feel that effect. It's pretty cool, like rig up a bunch of pulleys and hold a 5 kilogram mass with your 2 fingers. Like, wow, you really feel the difference, you know. Any other homework questions? That's it. Yeah.
So in this case, the equation and this setup would be 100.
Because again, intuitively, think of like, I think this is the easiest way to think of it. If you're going to lift this an inch, that means each one of these has to be an inch shorter, and those 4 inches go to this one. If you're ever trying to pull a car out of like mud or something, if you can rig up some kind of system like this, you know, I think we used it once to try to get a big rock out of the lake. I can't remember if it worked or not. Although that seems like sort of an important part of the story, doesn't it? Well, you attach one end to like a tree or something strong. You attach the other end to the car or the rock, and then it comes with you. But when you can actually just buy these setups. Like a real Black and Tackle is like a rigid box, and there's pulleys up here and pulleys down here, and so you don't spread it out. It's not spread out like this. It's spread this way, you know. And so the cable just goes over all these pulleys like this, and then a rope comes out the bottom.
Yeah, but wouldn't those be two bodies?
Yes, you're right. It needs to be 2 different bodies. Two. So one has, yes, it has to be 2 bodies. You're exactly right. And then the ropes go around. Question?
Yeah, how much force would those pulleys be like if you're trying to move a car, would you have to get some like industrial pulleys that wouldn't break under the force, or because they're spread out like that for a problem?
Yeah, they have to. It has. If you're lifting really big things, they have to be really strong. So yeah, you're not reducing. Well, you could figure it all out by just taking free body diagrams of the individual things. You know. So like in this case, this pulley here is, I guess, sort of taking half of that weight because the weight is spread out over 4 of these, and it has 2 of them attached here. So, so the way to do that is just whatever you want to see, like how strong it needs to be. Just take a free body diagram of that thing. You know what the cable forces are, and go from there. Okay, so now let's go to the next topic, rigid body kinetics. For particle kinetics, there was really only one equation of motion we needed, Newton's second law. Now we have 2 equations of motion. The first one is Newton's second law, and that says the net force is equal to the mass of the chosen object times the acceleration of the center of mass. And the center of mass thing is going to sort of become more key now. Since we've been doing particle stuff before, everything about the motion is been given as the center of mass, so we haven't had to figure out where that is, but now we're going to have to. So that's the first one. And then the second one is the rotational version of Newton's second law, the moment equation. And that says that the net moment about some point A is equal to the mass moment of inertia about A times the angular acceleration of the body. And actually, I sort of want to stress that this is an important part of this equation. So Newton's second law is done right there. That's all you need to know about it, as long as it's an inertial coordinate system. This one has restrictions on what that point A is. So where A is either, and there are two possibilities. Anyone remember what those are? I mentioned them just sort of in passing. Center of mass, yep. And the other one is fixed in the inertial coordinate system. All right, so both of these require an inertial coordinate system. What does that mean? There's two ways something can be non-inertial. One is accelerating. So let's say the origin is not accelerating. And what's the other one? That's right. The axes can't be rotating. Or the orientation of the coordinate system can't be changing in time. All right, so here's a question. Well, this is something important about this. So for the second possibility for the about point, the body there has to be a point on the body that's fixed in the inertial coordinate system. That's like the body connected to the ground by a pin joint or something, like a hinge. That doesn't have to be true. There doesn't have to be any point like that, like a boomerang, you throw a boomerang, there's no point of that that's fixed in the inertial coordinate system. Okay, so you can always use the center of mass as A, and you can't always find a fixed point. And so, like I'm always like, I try to just use the simplest, like forget it, like remember as little stuff as I can and, boil it down just so I don't have to remember as much stuff. Like I never use the quotient rule. I just use the product rule and so, and so this might seem like one of those cases where, well, if you can always use the center of mass as the about point, why even look for a fixed point? It turns out the math is a lot easier if you can find a fixed point. So still, if there's a fixed point, it's worth using it. And we'll do an example or two eventually where we'll do the calculation using a fixed point. We'll do the calculation using the center of mass, and you'll see how, what the extra stuff is that comes in from ignoring the fact that there's a fixed point, and it's just sort of a pain. Any questions about that? So that's kind of like going to be the underlying biggest idea for rigid body kinetics. All right, well, now we need to be able to calculate the center of mass. Obviously, the center of mass is important. So first we have to talk about calculating the center of mass. There's an integral definition for the center of mass. We're not going to use that, but I'm going to start with that definition. In 2D, to find the coordinates of the center of mass, it's equal to 1 over the total mass times the integral over the total mass of x, y, dm. And in 3D, everything's the same except now you have a z component too. If you're dealing with a homogeneous body, and homogeneous just means it's the same everywhere. So the same material everywhere. Then the center of mass is at the geometric center, which is called the centroid. The centroid doesn't have anything specifically to do with mass, but the centroid is at the same spot as the center of mass, unless you have, like if you have a material that's steel over here and wood over here, then the geometric center and the center of mass don't correspond. But and so we're going to do these calculations using centroids. And as you might imagine, they also have an integral definition. So in 2D, to calculate the centroid, x bar, y bar is equal to 1 over the total area times the integral over the area of x y, dA. And in 3D, everything's the same except the area changes to volume, and now we have three components on all the vectors. So we have x bar, y bar, z bar is equal to 1 over the total volume times the integral over the volume of x, y, z dV. And one thing you should keep in mind if you ever use this is that these coordinates x, y, z, so those are coordinates of an infinitesimal piece of this overall area or volume, okay? Sometimes you don't choose your, like in practice when you're calculating these, depending on the shape, you're usually not going to choose your infinitesimal area or volume to be infinitesimal in every dimension. You might choose it to be like if you're doing like a round shape, you might choose it to be an infinitesimal sliver of a, like a slice of pie with an infinitesimal angle, So in that case, there's not a single XY or XYZ that represents that entire piece. You know what I mean? And so these coordinates have to represent something about the piece. And in that case, that has to be the centroid of the infinitesimal piece dA or dV. I think it might be the case that I'm never going to have you use the integral definition. In statics, you spend a little more time on this. But there are a couple of things so there are two facts that usually make it possible to avoid that integral definition. The first one is that the centroid lies on any line of symmetry in 2D or plane of symmetry in 3D. And so in 2D, if you can find two different lines of symmetry, then those are going to intersect somewhere, and where they intersect is the centroid. 2D. So like in 2D, say like the Star Trek thing, that has a line of symmetry like this. And so the centroid has to lie somewhere along that line of symmetry. A rectangular shape has a line of symmetry there and a line of symmetry there. And so the intersection has to be the centroid. That's the center of mass symbol. And then same with ellipses and stuff like that. There's two lines of symmetry where they intersect is the centroid. A circle has, I can't think of any other 2D. Yeah, this is the only 2D shape that has this. There are infinitely many lines of symmetry, but that's okay because they all meet in the same spot, and so that's the centroid. And then it works the same in 3D. It's just planes of symmetry. So in 3D, if you can find 3 different planes of symmetry, they'll intersect at a point, and that point is the centroid. Okay. If you can only find 2 planes of symmetry, though in 3D, those intersect at a line, and then the centroid is on that line somewhere. And you still have to do the calculation of where along that line. Okay, the second fact is if you know the centroids of individual shapes, there's a sum formula for calculating the centroid of a complicated shape made of these individual shapes. And that's true in 2D and 3D. In 2D, it looks like this. It actually looks just like the integral definition of centroid, except in a finite version. So you have x bar y bar is equal to 1 over the total area. Instead of an integral, since these are finite things, we have a sum. So times the summation from 1 to however many shapes you have of coordinates of the centroid of the individual shape times excuse me, the area of the individual shape. This is the one we're going to use more. And then also in 3D, it's what you would probably come up with if you had to come up with a sum formula. It's 1 over the total volume times the sum from 1 to n of the centroid of the individual shape times the volume of the individual shape. We're not going to use that one as much. Man. We're not going to use that one as much. Because all of this stuff we're talking about right now only works for 2-dimensional rigid body kinetics. And you might ask why I didn't say that before when I introduced this. It's because I forgot, but I should have. So rigid body kinetics in 2D. Okay, and this is the last thing. So it's sort of funny, like normally, like when you talk about particle physics or whatever, you talk about 2D mostly instead of 3D because there's really no difference. And so it doesn't really help your understanding at all to just have a third component floating around and everything. They're exactly the same, you know. With rigid body kinetics, that's actually not true. 2D, we're going to use techniques that just straight up don't work in 3D, and I'll try to point out as we go when the things come up that make those so different. But 3D particle rigid body kinetics is fundamentally different than 2D rigid body kinetics, and you don't see that too much. So, okay, that's it.